Here are the answers for section 7-6. Question number 1. Part A, we're asked if this difference is rational or irrational. So if we try to simplify this up as much as we can we ever get the radical symbols to disappear and just get a rational number? For this first one, we can't. This is irrational. In part B, we're asked to give a decimal approximation of the answer. If you type it in the calculator and round it off, it's about negative 7.52. Number 3. Let's try to simplify this difference and see if we can get those square root symbols to disappear. We could rewrite our first term as 1/10 times the square root of 25 times 2. And we could rewrite the second term as 1/6 times the square root of 9 times 2. The reason I did that is because 25 is a perfect square and 9 is a perfect square. Let's rewrite again. The square root of 25 makes 5, and 1/10 times 5 is 5/10 or a half, and then we'll leave the 2 inside the radical symbol. Now this part here, the square root of 9 makes a 3, so if a 3 comes out of the radical symbol, then 1/6 times 3 is 3/6 or a half, and there's still a square root of 2 left inside. Now 1/2 square root of 2 minus 1/2 square root of 2 is just 0, which is a rational number. So this is rational. And we don't have to do part B because we already know the answer is exactly 0. Number 5. Let's try to do some rewriting on this. The cube root of 135 does not make an integer. But what if we factored 135? It can be written as 27 times 5. So let's rewrite our problem. The 135 is 27 times 5. Similarly, we can rewrite negative 40 as negative 8 times 5. The cube root of 27 is 3, and 1/3 times 3 makes 1 square root of 5. Over here, the cube root of negative 8 is negative 2. So if we minus a negative 2, that makes plus 2 cube root of 5. Oops, I lost my little index of 3 right there. Now we can add these together because they're like terms. 1 cube root of 5 plus 2 cube root of 5 makes 3 cube roots of 5. But we can't do any better than this. There is no way for that radical to completely disappear and make a rational number. So question A, this is irrational. And if we type this in a calculator, we get 5.13 if we round. Number 13, we're asked to simplify this difference. To simplify a difference involving radicals, we need to create like terms, like we had in those earlier questions. The 4th root of 80 does not make an integer, so let's try to do some rewriting on that. 80 can be written as 16 times 5. And I chose 16 times 5 because we can find the 4th root of 16 and get a nice result. Similarly, let's rewrite this one over here as the 4th root of 5 over the 4th root of 16. The 4th root of 16 is 2, and 5 times 2 makes 10, 4th root of 5. So this right here is how you rewrite this term. Now let's work on this second term. In the denominator, the 4th root of 16 makes a 2 in the denominator. So we have 9 over 2 times the 4th root of 5. Doing this is helpful because both terms now contain the same radical, 4th root of 5. These are called like terms. And we can combine like terms just like if they were variables, like they were both x's or something. So 10 minus 9 halves makes 11 halves times the 4th root of 5. Next, number 15. To simplify an adding and subtraction problem that involves radicals, we want to try to create like terms. We want to create the same kind of radicals. So let's work on this first piece. The square root of 4 makes a 2. X times 2 is 2x. And then this x here stays in the radical. Now let's work on this middle part. The square root of 25 is 5, and 25 times 5 is 125. Now let's do the square root of the x cubed. First, think about factoring x cubed as x squared times x. The square root of the x squared makes an x, but then this other x is going to stay inside a radical. Now this last piece, the square root of 81 makes 9. But on the x to the third power, again, we're going to want to think of it as x squared times x. We can take the square root of the x squared, making x, but then this extra x stays in a radical. These are all like terms. They all have the same radical part, so we can combine them. 2x minus 125x is negative 123x, and then when you add 9x, that makes negative 114x square root of x. Number 17, again, an adding and subtraction problem involving radicals. Let's try to create like radicals. Let's work on the first piece. 64 is not a number that you can take the fourth root of and get an integer result. So we need to do some factoring. Let's rewrite this as the fourth root of 16 times 4. And then keep the y to the 8th power. Now let's look at the middle term. 4 is not a number you can take the fourth root of and get an integer result. But you also can't factor 4 into anything that will give you an integer result either. So we're going to leave it as the fourth root of 4, y to the 8th. Now this last piece. I'm wondering if 324 is a number with a perfect fourth root. Let's find out on the calculator. 324 raised to the 1/4 exponent is a decimal. So since this doesn't work out to a nice answer, let's try factoring it. 324 is the same as 81 times 4. And I chose this pair of numbers because 81 does have a perfect fourth root. 81 is 3 to the 4th power. Next up, the fourth root of 16 is 2, and 2 times 2 is 4. The fourth root of y to the 8th is y squared. And then for this 4 right here, we'll leave it inside the radical. Now in the middle, the fourth root of y to the 8th is y squared. And then for this 4 here, we'll leave it inside the radical. Now this last piece, the fourth root of 81 makes 3. And for this 4 right here, we'll leave it inside the radical. Notice how all the terms have the same radical. So we can combine them. 4y squared minus 1y squared is 3y squared, and 3y squared plus 3 can be written as 3y squared plus 3. And then next to it, you put the fourth root of 4. Number 19. Let's try to create like radicals. First of all, does 625 have a perfect cube root? If you don't know the answer, take your calculator and go 625 raised to the 1/3 power. That makes a decimal. So let's try to rewrite 625. 625 is the same thing as 125 times 5. And I chose that pair of numbers because 125 does have a perfect cube root. It's going to turn out to be a 5. Now let's look at the variable. This power is not a multiple of this index. So let's do some factoring. We'll factor it as y to the 3rd times y squared. In the next step, at least we'll be able to find the cube root of y to the 3rd. Now in the middle, there's not really any rewriting that can be done at this point, so I'm just going to copy this down. Now here on the end, negative 40 does not have a perfect cube root. So let's factor negative 40. Now there are different choices of numbers that times together to make 40, like 4 times 10, 8 times 5, 20 times 2. Which should we use? I'm going to use negative 8 times 5. And I picked that because negative 8 is a number that you can take the cube root of. This right here is a y squared, so let's just copy that down. Okay, next step. The cube root of 125 makes 5. The cube root of y cubed makes y. This 5 and this y squared will have to stay in the radical symbol. Now here in the middle, the cube root of y cubed makes y, and a y out front times another y makes y squared. But the cube root of 5 will have to stay inside the radical symbol. Now here on the end, the cube root of negative 8 makes a minus 2. But this 5 and this y squared will have to stay inside the radical symbol. As we look at this right here, not all three terms have the same radical. But this one here and this one here do, so they can be combined. 5y minus 2 makes 5y minus 2. And that's times to that radical symbol. And then separately from that, we have this radical here in the middle. Okay, next, number 27 changes the directions. We have an equation, and we're asked to find all real roots. That means to solve for x. If we want to solve for x, it would help to have all the x terms on the left side. So let's add this one here to make it move to the left. I'm going to add x square root of 27 to both sides. We will have x square root of 3 plus x square root of 27 plus the square root of 6 equals the square root of 150. Since we're collecting the x terms on the left, let's move this square root of 6 to the right side by subtracting it. Now we have x square root of 3 plus x square root of 27 equals the square root of 150 minus the square root of 6. Let's see if we can combine these together by getting like radicals. Let's rewrite the 27 as 9 times 3, because we can find the square root of the 9. We have x square root of 3 plus 3x square root of 3 equals. What I did was I took the square root of 9, getting a 3, and then I said x times 3 makes a 3x. And then this 3 stays in the radical. Over here on the right side, let's do a little bit of combining there if we can. Let's factor the 150 as 25 times 6, because the square root of 25 makes 5, and then leave the 6 in the radical, and then here's that minus square root of 6. Notice how that makes some like terms here. And even on the other side, there are some like radicals. So next up, x plus 3x makes 4x times the square root of 3. On the right side, 5 square root of 6 minus 1 square root of 6 makes 4 square root of 6. We're trying to get the letter x alone. Let's start dividing away these numbers that are by it. First, divide by 4 on both sides. We get x square root of 3 equals the square root of 6. Now divide by the square root of 3 to get the x alone. We have the square root of 6 divided by the square root of 3. Now let's put them under one radical symbol, getting the square root of 2. In the original directions, we were told that x is greater than 0, so we only want to take the positive version of the square root. We're not going to put a plus minus sign with this answer. Number 37. We're given this equation and we're told numbers to use for a and b with the purpose of showing that this is a false statement, that you can't take the square root of a sum and split it up into two pieces like we often do with multiplication problems. That factoring thing only works with the multiplication. not with addition. Let's show why. This would be the square root of 9 plus 16. And again, we're trying to show that it's not equal to the square root of 9 plus the square root of 16. 9 plus 16 is 25, and the square root of 25 makes 5. But over here we have 3 plus 4, which is 7. So you can see how when you have these two things added together, it is not okay to split it up into two adding terms. Now the review assignment. We're going back to the section where we're first learning to simplify radicals. Again, there are 4 requirements you've got to follow. This one here is a negative exponent. So let's first take care of that by doing the reciprocal. Now we've created a fraction. So let's take care of the fraction by splitting into separate numerators and denominators. And the fifth root of 1 makes 1. Down in the bottom, I'll rewrite what we have. We can't leave a radical in the denominator of a fraction, so let's rationalize this. This power does not match this index, but let's multiply top and bottom by something that will cause it to be a multiple of the index. How about we times by the fifth root of k to the fourth? In the top, we get the fifth root of k to the fourth all over the fifth root of k to the 10th. So our final answer is the fifth root of k to the fourth all over k squared. Number 28. Again, we have a negative exponent. So let's first take care of that. Then separate this into a separate numerator and denominator. And the fifth root of 1 makes a 1. This is very similar to the one we have right above. Notice how similar these things are. So we want this to be the fifth root of m to the 10th, because then the power would be a multiple of the index. So let's times top and bottom by the fifth root of m to the 3rd. That makes the fifth root of m to the 3rd over the fifth root of m to the 10th. On the top, we have fifth root of m to the 3rd divided by m squared. Number 29. This one also has a negative exponent situation. Let's take care of that. Next up, is 128 a number that has a perfect sixth root? Let's use the calculator to find out. 128 raised to the 1/6 power. Nope, that makes a decimal. So maybe factoring will get us somewhere on that one. 128 is the same as 64 times 2. Does 64 have a perfect sixth root? It does. 64 is 2 to the 6th power. So let's rewrite the top as the sixth root of 64 times 2. And then for now, keep the y to the 12th in there. In the bottom, we'll keep that as it is right now. The sixth root of 64 is 2. The sixth root of y to the 12th is y squared. And then this 2 right here will leave inside the radical. Okay, we got the top looking pretty good, but in the denominator we still have a radical. So we need to do that technique of rationalizing. This power is not a multiple of this index of 6. But if this 8 was instead a 12, then it would be a multiple. So let's multiply top and bottom by the sixth root of x to the 4th power. Now we have 2y squared times the sixth root of 2x to the 4th, all divided by the sixth root of x to the 12th. But the sixth root of x to the 12th is x cubed. Number 30. This has one of those negative exponents in it. So let's do some rewriting. Next, we need to check if 729 has a perfect sixth root. I don't have my sixth roots memorized, so I definitely need to calculate on this. 729 raised to the 1/6 exponent makes the number 3. So that does work out nicely. The sixth root of 729 is 3, and the sixth root of v to the 18 is v to the third. I got this exponent by dividing the power by the index. In the bottom, let's just keep it the same for now. How do you rationalize this? This 9 is not a multiple of this index of 6. But if this was a 12 instead of a 9, it would be a multiple. So let's multiply the top and bottom by the sixth root of t to the third. We get 3v cubed, sixth root of t to the third, all over the sixth root of t to the 12th. But the sixth root of t to the 12th is t squared. Number 31, we have a multiplication problem right in there. So 5 times 3 makes 15. And now inside our radical, we can do some multiplying. Negative 16 times negative 2 makes 32. And a times a squared makes a cubed. And b squared times b makes b cubed. 32 does not have a perfect cube root, but maybe we can factor it. 16 times 2 won't help us because 16 doesn't have a perfect cube root. But using 8 times 4 would help because 8 does have a perfect cube root. So let's think of 32 as 8 times 4. The cube root of 8 makes 2, and 15 times 2 is 30. The cube root of a cubed makes a. The cube root of b cubed makes b. And then left inside the radical is that factor of 4. Number 32, another multiplication in here. 3 times 5 makes 15. And then inside the cube root radical, we can also multiply. Negative 12 times negative 3 is 36. X times x squared is x cubed. Y squared times y is y cubed. Now the cube root of 36, that doesn't make anything nice, that's a decimal. But maybe we can rewrite 36. We have to have one of the numbers that we use to rewrite it be something that you can take the cube root of. So 9 times 4 doesn't help us. 12 times 3 doesn't help us. 2 times 18, nope, that's still not helpful. I've tried different combinations of numbers, but I can't think of a way to factor 36 where one of the numbers is a perfect cube. I guess we'll just have to leave 36 in the radical. So our answer is 15, and then the cube root of x cubed makes x, the cube root of y cubed makes y, and the 36 is going to have to stay in the radical. Number 33, another timesing problem. So the things that are in the radical, we could actually times them. 9 times 27 makes 243. And g times g is g squared. And h to the 4th times h is h to the 5th. Now, is 243 a number you can take the 4th root of and get an integer? I'm going to take a calculator and go 243 raised to the 1/4 power. Nope, it's a decimal. Let's try to factor the 243. 243 is the same as 81 times 3. And I'm using that pair of numbers because 81 is something that we can find the 4th root of. Leave the g to the 2, but factor the h to the 5th as h to the 4th times an h. The 4th root of 81 is 3. The 4th root of h to the 4th is h. The other things are going to stay in the radical. There's a 3, and there's a g squared, and there's an h. Number 34, another timesing problem. So let's multiply inside those radicals. 5 times 125 is 625. C to the 4th times c squared is c to the 6. D to the 7 times d to the 3rd is d to the 10. Can we find the 4th root of 625? On a calculator, I go 625 raised to the 1/4 power. That just makes 5. So yeah, the 4th root of 625 is just a 5. Now for these variables, let's factor them. The c to the 6th, think of it as c to the 4th times c squared, because you can find the 4th root of c to the 4th. It just makes a c. And for the d to the 10th, think of it as d to the 8th times d to the 2. The 4th root of d to the 8 is d squared. So left inside the radical is a c squared and a d squared. This one here and this one here. Number 35, we have a division problem. So let's divide. 8 divided by 4 makes 2. And then inside the radical, we can also divide. 54 divided by 3 makes 18. And x to the 5th divided by x to the 1st makes x to the 4th, using the rule about subtracting exponents. Now you can't take the square root of 18 without getting a decimal, so let's do some factoring. Think of 18 as 9 times 2. We can leave the x to the 4th because it is an even power, and we're doing an even root here. So the square root of 9 is 3, and 2 times 3 is 6. The square root of x to the 4th is x squared. And then this 2 right there stays in the radical. Number 36, let's also do some dividing. 5 divided by 15 reduces to 1/3. Now those radicals. 250 divided by 5 makes 50. And y divided by y cubed makes y to the negative 2. Which eventually I'm going to have to move back into the bottom anyway. So we have the square root of 50 over 3 times the square root of y squared. The square root of 50 can be rewritten as the square root of 25 times 2. The square root of 25 makes 5. And the square root of y squared makes y. So here's the final result.